Hi everyone, welcome back to Math with Amala. This part is part number 3 of grade 12, chapter number 1, Relations and Functions, and this contains exercise 1.1. We have to determine whether each of the following relations are reflexive, symmetric, and transitive. First question, relation R in the set A equal to set 1, 2, 3, etc. 13, 14, defined as R is equal to set of all xy such that 3x minus y equal to 0. Here I have listed the possible values of x and y's. Then you get the relation R is equal to 1, 3, 2, 6, 3, 9 and 4, 12. This is not reflexive, not symmetric, not transitive because there is nothing like AA or AB implies BA or AB implies, AB and BC implies AC. The second one, set of all xy such that y equal to x plus 5 and x less than 4. Here the possible values for r from the natural number set n is 1, 6, 2, 7 and 3, 8. Here it is very clear that it's not reflexive, not symmetric, not transitive since we can take only up to 3 because the number is x is less than 4. Third one, set of all xy says that y is divisible by x and x and y are from 1, 2, 3, 4, 5, 6. Here we can have the numbers like 1, 1, 2, 2, 3, 3, 4, 4, 5, 5 and 6, 6 because these are divisible by itself. 6 by 6, 5 by 5, 4 by 4, it's possible. Likewise, 2 by 1, 3 by 1, 4 by 1, b divides a. So we can write like y divides x. Hence 5 by 1, 6 by 1, 4 by 2, 6 by 2 and 6 by 3 are all possible. Let's check the reflexivity. 1, 1, 2, 2, 3, 3 is there, so hence it is reflexive and 4, 4, 5, 5, 6, 6 are also there. Now the symmetric property a comma b belongs to R implies b comma a belongs to R. Is it possible? Let's see. 1 comma 2 is there. Is there 2 comma 1? No, it's not there. Likewise 2, 4 is there but no 4, 2. Hence it is not implying here. Hence we can say that it is not symmetric. Then let's check the transitivity. In this one, we have to take some xy where y divisible by x and also yz where z divisible by y implies xz. Okay, so 1, 4, 4, 4. This implies 1, 4. Hence it is transitive. Next one, relation R in the set where R is equal to set of all xy such that x minus y is an integer. X minus y is an integer. Hence we can say take the values like 1 minus 1, 2 minus 2, 3 minus 3. That is a minus a equal to 0. 0 is an integer. Hence it is reflexive. 1 minus 2 equal to minus 1. This belongs to z. And 2 minus 1 is equal to 1. This is also in z. Hence it is symmetric. Next 1 minus 2 equal to minus 1. It is there in z. 2 minus 3 is there in z. And also 1 minus 3 is there in z. Hence it is transitive. Hence it is an equivalence relation. Now let's do the last problem using a table. Here I have given the relations and we can give the ticks for reflexive, symmetric and transitive if they are holding the conditions. First one, x and y work at same place. It is reflexive since x and x is related here and symmetric because x is related to y related to x. Because x and y work at same place means y and x also same place, then it is symmetric and transitive. Then with the same logic we can say they live in the same locality, hence reflexive, symmetric and transitive. Next, x is exactly 7 centimeter taller than y. Here x is related to x. Is it possible? There we need a comparison, so we can't do with the same one. So x is not related to x. X is not exactly 7 centimeter taller than x. So it is not reflexive. X related to y, y related to x. Is that possible? No. If it is taller than 7, it cannot be taller than the previous one in its reverse. So that is not symmetric. Then for the transitivity, x related to y, y related to z, it's possible. But x related to z is not possible. Okay, so that's also not transitive. X is wife of y. X cannot be wife of itself or that person itself. Then it is not possible, not reflexive. then x related to y, y is not related to x, and then x related to y, then y related to z, and it doesn't implies x related to z. Okay, these are actually against the logic. Hence, it is not reflexive, not symmetric, and not transitive. Next one, x is father of y. Hence, x cannot be father of himself or herself. Then it is a wrong statement. Then x related to y cannot be related to x in return. So that also not possible. X can be father of y and y can be father of z, but it doesn't means that x can be father of z. Okay. Now, which means it is neither reflexive nor symmetric or nor transitive. Next, move to the second question. Here we have the relation a less than or equal to b square for the real number set. It is a false statement. A is less than or equal to a square is false. It's not possible. Then it's not R, that is reflexive, not reflexive. A less than or equal to b square doesn't imply b less than or equal to a square. Hence it is not symmetric. Now a less than or equal to b square comma b less than or equal to c square does not implies a less than or equal to c square. Hence it is not transitive also. Let's move to the third question. The relation is b is equal to a plus 1. We have to check whether it is reflexive, transitive or symmetric. Okay. R is equal to set of all AB such that B is equal to A plus 1. And the given set is set 1, 2, 3, 4, 5, 6. So let's see R is equal to, what are the possible values for R? Values for R are 1, 2. Then because B and A, B is equal to A plus 1, 2 equal to 1 plus 1, 3 equal to 2 plus 1. 4 equal to 3 plus 1. Likewise, you will get 3, 4, 4, 5 and 5, 6 in the set. Now we can see that A is not equal to A plus 1. Hence it is not reflexive. Now B is equal to A plus 1. Does it implies that A is equal to B plus 1? So it is not symmetric. Next we consider the case of transitivity. B is equal to A plus 1 and C is equal to B plus 1. Here this B can be replaced with A plus 1. Then C is equal to A plus 1 plus 1. Okay. C is equal to A plus 1 plus 1, that is A plus 2. Which is actually not in the case of transitivity. Hence we can say that it is not transitive. We need something in the form of A plus 1. It is not possible here. Now let's move to the fourth question. Show that the relation R in R, the real number set defined as R is equal to set of all AB such that A less than or equal to B is reflexive, transitive and not symmetric. Here A less than or equal to B is the relation. It's obvious that A less than or equal to A always, hence it is a reflexive relation. Then A less than or equal to B, B less than or equal to A is a false statement. It's not possible since it is an inequality. Then A less than or equal to B, B less than or equal to C implies that A less than or equal to C. We can give a transition here because A to B and B to C is possible, which means A to C is much possible. Hence it is transitive. Next, the fifth question. Check whether the relation R in the real set defined by R is equal to set of all AB such that A less than or equal to B cube is reflexive, symmetric or transitive. We have to check here. A less than or equal to B cube is the relation. A less than or equal to A cube, it's obvious. Only in some cases. For an instant, we can take 1 less than or equal to 1 cube. It is there because that equal to symbol is there. And we can say like 2 less than or equal to 2 cube. It's okay. But if we take A is equal to 1 by 2, it's cube. 1 by 2 is not less than or equal to 1 by 8. Okay, 1 by 2 is greater than 1 by 8. It's not always reflexive, but in only some cases it's reflexive, but we can't consider that. Hence it is not reflexive. Then the next one, A less than or equal to B cube, B less than or equal to A cube. Is this possible actually? Actually, this is not possible. This is a false statement, hence it is not symmetric. Let's give some example with A is equal to 1 and B is equal to 2. Here 1 less than or equal to 2 cube. It's true. And 2 is not less than or equal to 1 cube. So we can say it's not symmetric. Next one, a less than or equal to b cube, b less than or equal to c cube. We can check whether it is true for a less than or equal to c cube for the transitivity. Let's take 3 examples. A equal to 1, b equal to 2, c equal to 3. It's a random example. So 1 less than or equal to 2 cube, 2 less than or equal to 3 cube. But it is true that 1 is less than or equal to 3 cube. We can have some other cases which are not having this property or surety. Let's take the examples for a equal to some number 9. Let's take a is equal to 9 and b is equal to some 3. Then 9 is less than or equal to 3 cube. 3 cube is 27 and b is 3 and c can be taken like some number related to which is less than 9. Okay, if we take something greater than 9, let's take 4 cube, it's 64. So it is holding here or it is transitive in this case. But if we take some numbers which is less than like 2 cube, it is 8. So 9 less than or equal to 8 is not possible. So let's take one more example. 12 less than or equal to 3 cube, that is 27. Then 3 less than or equal to 2 cube, that is 8. Here 12 less than or equal to 8 means it's not possible. It's not a true case, it's false. Hence we can say it is this transitivity is not holding for all the elements a, b, c in the real number set. Okay, here 9 less than or equal to 8 is not possible. Also 12 less than or equal to 8 is not possible. Sixth question, we have to show this R is symmetric and neither reflexive nor transitive. It is not reflexive because 1 1 2 2 is not there and 3 3 also is not there. Then not transitive because 1 2 2 1 is there but 1 1 is not there. And it is symmetric. 1 2 2 1 2 2 1 is there, hence it is symmetric. In the question number 7, we can see that the relation is set of all xy such that x and y have same number of pages and we have to prove it as an equivalence relation. X is related to x because it have the x itself have the same number of pages, and x is related to y means it is actually related to y is related to x because it is the same book. Then x and y are related and y and z are related means also x and z are related because they are connected alternatively. Let's move to the 8th question. R is equal to set of all a b such that modulus of a minus b is even, and that means if we take the a minus b as the negative, then the mode will cancel the negativeness and you can get only the positive values of the relation members. Now let's move to the equivalence relation. We can prove it here. Modulus of a minus a is 0. It's an even number, hence it is reflexive. If modulus of a minus b is an even number, of course it's reverse, that it is commutative. Its modulus of b minus a is also even, hence it is a symmetric relation. Now modulus of a minus b is even, modulus of b minus c is even, implies modulus of a minus c is even. Because we can have that these two relations which are coming inside are already, hence we can say that a minus c, modulus of a minus c again gives us the even number. So we can say that it is reflexive, symmetric and transitive, hence it is an equivalence relation. We have proved that it is an equivalence relation. Now let's consider the sets 1, 3, 5 and 2, 4, and we have to find whether they are connected inside and whether they are connected to each other. Okay, so modulus of 1 minus 3 is 2, modulus of 3 minus 5 is 2, modulus of 1 minus 5 is 4. These are all even numbers, hence it is okay inside the set 1, 3, 5, that is even numbers. Then for 2 and 4, it is an even number, but it's not possible in the case when we take elements from first set and second set. 1 minus 2 is 1, 3 minus 4 is 1. Thank you all for watching the video. Please be stay tuned for the next part.